Rather than follow along this path any further with the driving experiment, I'm going to shift gears a little bit and jump into another set of experimental data. 1% of humankind suffers from the debilitating illness of schizophrenia. This is, of course, a very important theme of study around the world, but it is also a topic much explored at Olin. And Abby Garrity was a student. She worked with the Olin researchers on schizophrenia, and this led to this publication in the American Journal of Psychiatry, which, by the way, was in the news just yesterday as the journal that released the results about the atypical antipsychotic medications in children, along a big study on that. This is a different task in this study. These data are no longer the virtual driving task, but rather a very simple button-pushing task. You listen for a tone of a certain pitch and push a button. There are other tones are playing, though, in the background that are somewhat distracting. We're going to jump directly to the sound, cutting right through all the other discussion of what's going on with components. And what I'm going to do is play for you two pairs, a pair of healthy control subjects and a pair of brains of individuals with schizophrenia. You will listen to each pair. That's your training session. And yes, this will be on the midterm, because then down below you will take the schizophrenia soundtrack quiz and see if you can tell, using your ears alone, who is who. So let's begin with a healthy subject. This is about 30 seconds. Now, an individual with schizophrenia. A healthy subject. And a patient. Now, which is which? Show of hands. How many of you guess healthy? How many of you guess schizophrenia? Okay. The answer as a healthy subject. On to the next. How many of you say healthy? Schizophrenia. finally this last one. Healthy? Patient. All right. Just point out, you did well. I was pointing out that you had no patient histories here. You had no listing of symptoms, no medical history whatsoever, not even images of the brains of these patients, no other data whatsoever. And you were quite capable most of the time in making this sort. What were you listening to? What was it that we were picking up on? Doing this suggests different ways to look at these data that might not have been so apparent to begin with. Well, one thing that at least I hear, I think, is that it seems to me that the patients are oscillating more rapidly. There's a general sense of greater speed on those. And so to take just two from the set, we can display this oscillation. What I've done is I've sorted the components now from the fastest oscillating at the top to the slowest oscillating at the bottom. Indeed, visually you can see that, and you can actually measure that, you can count them. There are many different ways to do this, but here's a kind of simple way of doing this. If you imagine the component going above and below the mean of its own activity, and if that mean is 0, then we're talking about as it rises, it crosses 0, as it falls, it crosses 0. So it's a way of counting over the experiment duration, how many times the intensity goes up and down. And if we, again, have them sorted in this way, we find that at every comparable component point, the patient, in this case, oscillations are much faster than that of the control subjects, indeed almost twice as fast in this comparison. Now, Abby Garrity and co-workers in her paper brought out this exact difference in oscillation, difference in frequency of oscillation with respect to one crucial component known as the default mode network, and discussed it in a very interesting way, what that could mean. What we observe here, though, is that it's not just one component, that there is a global difference in oscillatory frequency in all the components in these patients. And indeed, if we graph in each of 16 patients, they are, in general, their means are significantly different. And the crosses then are the individual data points, the median oscillatory frequency of these. A couple of things.